Ja, hallo und herzlich willkommen bei Wissenschaft fürs Wohnzimmer heute. Und heute switchen wir direkt mal wieder auf Englisch. Wir hatten es lange nicht, einen englischen Gast bei uns, aber heute ist Emma Smith bei uns. Von daher, welcome Emma. So welcome to Science for the Living Room. I think you had a better translation for this. You should tell us later. Yeah, so as usual, we will first present ourselves, the ones here with Emma. So I'm Janine. I'm working at the Alfred Wegener Institute as a postdoc. I'm coordinating a project and working in a project where we study the ocean heat fluxes towards the Greenland glaciers. And in the same section as me is working also Rebecca, who can say something about herself next.
Yes, hi, I am Rebecca and I also work at the Alfred Wegener Institute. With Janine, actually, we share an office, or we did before March. And I am sort of a physical oceanographer, which means that I use sort of measurements and observations from the ocean to try and work out how it all works, in particular, why the glaciers in the northeast Greenland are melting and how warm water gets to them. And it is, yeah, it's pretty neat and very prescient. And so it's great to have an opportunity with Emma, for instance, today to talk about our work and let you all into it.
Okay, yeah, good evening. I'm Nico. I'm a PhD student at RV and I'm working in the glaciology section, looking at ice cores, mainly from Greenland, and analyzing the microstructure and the impurities inside the ice to understand the flow of ice better. And I've been sort of working together with Emma a little bit, and she's being a teacher for me on the field trip once. So I'm quite happy to have her here today, and I'm interested to see her talk. So Emma, I think it's your turn now.
Hi, yeah, thank you very much. I'm Emma Smith. I'm a postdoc at the University of Leeds. And yeah, I used to work at the Alfred Wegener Institute. So that's how I know a few of the people here. And today I'm going to talk to you about Antarctica, which is the area I mostly work in, and particularly about one glacier in Antarctica that we think is really, really important. So I'm just going to start sharing my screen. Cool. Okay, yeah, so the title of my talk today is Thwaites Glacier, the keystone of West Antarctica. And hopefully by the end of this talk, you'll understand what I mean by the keystone of West Antarctica.
Emma, I think you need to switch the screens.
How does that look?
That's much better, lovely.
There's always a technical glitch. Okay, so yeah. And just to give you a small introduction to Thwaites Glacier, we have the background of this slide here. And in purple, you can see the area we call Thwaites Glacier highlighted. And it's about the size of Great Britain. So it's a really, really large piece of ice. But I'll talk to you a little bit more about that and where it is in a moment. But first of all, I just wanted to point out that it's really timely that I'm giving you this talk today, because this week is Antarctica Week. And Antarctica Week is a celebration of the signing of the Antarctic Treaty, which happened in 1959 on the 1st of December. And the Antarctic Treaty is what enables us to do our work in Antarctica, to go there for science, to collaborate with other countries peacefully, and to work across the whole continent with the help of lots of different nations. And there are lots and lots of different rules in the Antarctic Treaty, but the one I think is most important is just this idea that it reserves Antarctica as a natural place devoted to peace and science. So you're not allowed to go there to claim land or to dump waste or to harm the natural environment in any way. And because it's Antarctica Week, there are, sorry, one moment, there we go, a series of talks on this week. If you're interested in finding out more, then I'd really recommend going to this website, thwaitesglacier.org. And I'll put this up again at the end so you can see, but this is just an example of a few talks that are taking place tomorrow. all aimed at everybody and anybody. So children, families, anyone who's interested in finding out about work in Antarctica. Okay, so Antarctica is down here at the bottom of the world. And of course, it's the home of these lovely guys here, these penguins. But unfortunately today, I'm not going to be talking to you about penguins. I'm going to be talking to you about the thing they're standing on, the ice, and why it's so important for all of us. So let's take a slightly closer look at Antarctica. So this here is a map of Antarctica. You can see it's a whole continent. It's completely covered in ice and it's surrounded by ocean, shown here in blue. And the whole continent pretty much is covered in a thick ice sheet. And by thick, I mean several kilometers in some places. So it's a lot of ice. And around the outsides, so between the ice and the ocean, we have these areas in white, which are our floating ice shelves. And I'll explain a little bit later why these are so important. And I think one really key reason we're so interested in Antarctica is there's enough ice on the continent that if it all melted, it would raise global sea level by 60 meters. So that's a huge, huge amount of sea level rise and something that we should definitely pay attention to. But when I say there's enough water to raise global sea level by 60 meters, that's just a potential. It's not going to happen tomorrow. But what we need to know is where is it happening? How is it happening? And how fast is it happening? And that way we can reduce the uncertainty around the future of our planet and the future of our planet with respect to sea level rise. So just before I carry on, I think it's important to cover what it is or how it is that ice moves from Antarctica, from the continent out into the oceans. So this is a map here of the ice flow velocity, so the speed that ice is moving on Antarctica. And you can see the colours that are in red and purple are areas that are moving really fast. And the colours that are sort of green and yellow and peach coloured areas moving really slowly. And it's these fast flowing kind of veins or rivers of ice, as I like to call them, that are the pathways that move ice from the centre of the continent out into the oceans. And these are called, well, they have two names, ice streams and outlet glaciers. And it's this one down here in the black box, which is Thwaites Glacier. And that's the glacier I'm going to focus on for today. So I said we needed to work out where Antarctica was losing the most ice. And one way we can do this is using satellite observations. So satellites orbiting Earth can measure the amount of ice being lost from Antarctica. And they've been doing this over a long period of time, about 20 years, actually a little bit longer than that. But this time series I'll show you is since 2002. And I'm just going to show you a little video which will change colours depending on how much ice is being lost, and it will show you where there's a lot of ice flowing out from Antarctica into the oceans. So if you watch out for the colours that start to go red or the areas that start to go red over time, you'll see what I mean. So I'm just going to play that now. So we can see in 2003, we're starting to get lots of ice being lost in this area here and little bits elsewhere around the continent. But as we move forward through time, we can really see that this area, which is where Thwaites Glacier is losing more and more and more ice, much, much more than anywhere else in the continent. And that's really worrying. It's a really, really large amount of ice it's losing, and it's getting more and more each year. So although this time series ends in 2016, I can tell you that it keeps going on and it keeps getting more and more. We have calculated that the average mass loss is about 125 gigatons a year. So just to give you an idea, a gigaton of ice is enough to fill 400,000 Olympic swimming pools. So if you've got 125 gigatons, it's a huge, huge amount of ice. But what does that mean for global sea level? Well, if we look here at this graph of the total amount of contribution to sea level rise from Antarctica, we can see it's around about 7 millimeters in total since 1992. And if we split it up into these 3 different areas of Antarctica, so West Antarctica, which is where Thwaites Glacier is, Antarctic Peninsula, which is this part up here, and East Antarctica, which is this big, big part here, you can see the majority of it's actually coming from this area of West Antarctica. So it's really an area of concern and an area of interest for us. So we have a clue already as to why we're losing a lot of ice from this area of Antarctica. If you look on the left here, there's your map of Antarctica with Thwaites Glacier marked. And this map on the right is what Antarctica would look like if you took all the ice off it and looked at what was underneath it. So you're looking at the bedrock of the continent underneath. And the area in the red box is the area we call West Antarctica. And if you look at this area, you can see there's a lot of these dark blue colours, and that means it's very, very far below sea level. So blue colours are below sea level, green is kind of around sea level, and the red and kind of yellow and brown are above sea level. So this area here, most of it is below sea level. And even more importantly, it's actually deeper in the middle than it is at the edge. So your ice is sitting on top of this bedrock that's really far below sea level. So why is this important? Well, the ice sits on the bedrock and it's the weight of that ice that keeps it in contact with the bedrock. So you want lots of ice, you want really thick ice in order for it to stay in contact and not just start floating. When it gets thinner, it starts to float. And that's when you get these ice shelves I mentioned at the beginning, the floating parts. So it looks a little bit like this. You have here your ice sitting in contact with the bedrock. Then you have a boundary, so it's a virtual boundary, but it's what we call the grounding line, and that's the boundary between the ice that's sitting on bedrock and the ice that's floating on top of the ocean. And your ice is flowing from inland outwards into this floating ice shelf. Now, this floating ice shelf acts as a kind of barrier. It helps to hold the ice back and keep it on the continent. But it's also floating on the ocean, which is warm. And when I say warm, I mean relatively warm. It's very cold, but it's warmer than ice. And because it's sitting on the ocean, it's being warmed and melted from underneath. Now, as it gets melted, it starts to get thinner and the ice behind it can flow faster out into the ocean. But as the ice behind it flows faster, it also gets thinner. It's a little bit like stretching pizza dough, for example. If you're rolling out a pizza, the more you stretch it and the faster you pull it apart, the thinner it will get. And when it gets thinner, as we have written up here, it starts to float. So what eventually happens is this part that was previously sitting on bedrock has got so thin that it starts to float. And this grounding line, this area between the ice on bedrock and the floating ice, moves further back. But when you have a situation like you do in West Antarctica, where the bedrock is deeper in the center, it's going to keep moving back and back and back into deeper and deeper bedrock. So it's going to need to be thicker to stay in contact, but it's getting thinner, which means more and more of it's floating and more of it's being melted by the ocean underneath. And so you can see this is a bit of a runaway system. It moves back into deeper bed, which it can't sit on. So it gets lifted off, it starts to float, which means it can be more easily melted. So this is a system that can change very, very quickly, very rapidly. And within a short amount of time, lots and lots of ice can flow from the continent out into the oceans.
So Emma, one quick question to that. So what do you mean by short amount of time? What kind of timescales are we talking about there?
So that's a really good question. And that's exactly what we're trying to answer with the project that I'm working on, because there are so many different things that contribute towards it. So there's the ocean, there's the ice, there's the cavity, which is the part underneath the floating ice. There's the material that the bedrock's made up of. So I can't really put a figure on that, but that's what we hope we can find out with this project.
Okay, great. And just one more thing I want to mention also to people watching here. You can also always ask questions in the chat, and then we will pick them up and ask Emma either during her talk or afterwards.
Cool, thank you. Yeah, I'm very happy to answer any questions as they come in. Yeah, this is what I mean when I say that Thwaites Glacier is the keystone of West Antarctica. So a keystone, for those who aren't familiar with the term, is this stone in the middle of a bridge. And it's the stone that keeps everything together. So without this, the arch of the bridge would collapse. And so you really, really need this one piece to keep it all in place. And Thwaites Glacier is that keystone in West Antarctica. So it's the most unstable part of West Antarctica, and it's also the part that's holding it together. And what I mean by that is it's the place that's losing the most ice, and it's losing it very quickly. It's draining an area. So you can see this is a map just zoomed in of Thwaites Glacier, and this dotted line is the outline of the area it drains. So all of this ice here leaves Antarctica through this glacier. And that area is about the size of Great Britain. So it's really, really big. And since the 1990s, it's doubled in rate. So it's losing twice as much ice as it was 30 years ago. And this diagram also gives us a bit of a clue as to why that's happening. So out here, you have the ocean. This black line is the edge of this floating ice shelf. And this white line is the edge of the ice that's sitting on land. And the red colors here tell you the temperature, or the temperature of the ocean, the water that's underneath or coming into this ice shelf. And you can see that in Antarctic terms, this is quite warm water. And it's certainly much warmer than the ice. And in this area, we're seeing lots of this warm water coming up right to the front of this floating ice shelf and melting it from beneath, which is causing the process that I spoke about before. So how are we going to find out how quickly this is happening and how we might expect it to change in the future? We are going there with 8 different projects to look at all different parts of this system. And because Thwaites Glacier is really difficult to get to, and it's a really big effort to get there, this is a big collaborative project called the ITGC, or the International Thwaites Glacier Collaboration. And you can see here, there's 8 different projects going on in different parts of the system. So we've got a couple of projects going on out here to measure ocean properties, one on the floating ice shelf, some up in the mountains to look for evidence of the history of this area, and projects also on the grounded ice, so on the bit that's sitting on the bedrock, to try and understand that better. And it's a big project where we're using lots of different techniques to try and get the most information. So I mentioned before that we can take measurements using the satellites, but we also can't do a lot of things using satellites. So sometimes we really need to go there with a ship and measure properties of the ocean. We also will be drilling through the ice shelf here, the floating ice, and looking underneath it, sending little submarines, little vehicles in to have a look, and I'll speak a little bit more about that later. And also on the surface of the ice, we can actually make measurements through the ice to look below it, and that's the project I'm mostly involved in. So the project I'm involved in is called Time, and it's this one here in the shear margin of the glacier. And what we want to do is look through the ice and see what's beneath it and understand what the structure of the ice in that area is. And the reason the shear margin is so interesting is it's the boundary. I think we have it on the next slide. Yeah, it's a boundary that provides lateral drag. And by this, I mean it resists ice flow. So this map on the right here is again showing the ice velocity. So blue colors are where the ice isn't moving very much, red where it's moving quite a lot. And we want to look at this boundary between the fast and the slow ice, because this boundary really holds the ice back. Once it starts to flow fast, it provides some friction and stops it going too fast. And so that will help us understand the time frame of the collapse of this part of Antarctica. And the reason this particular boundary is so interesting is there's no clear reason it's where it is. Normally these things are in areas where the fast flowing ice is in a dip, where it can move faster because it's thicker, and the slow flowing ice is much thinner and colder and shallower, but this isn't the case here. So how are we going to look through the ice and see what's going on underneath it? we are going to do something very much like an ultrasound scan on the ice. So, for example, when you have a problem with your shoulder, you might go to the hospital and they'll use ultrasound waves. They'll put those into your shoulder. Those waves will bounce back off your muscles, off your bone, and you'll be able to see an image of what's going on inside your body. We do exactly the same, but we use audible sound, and the sound source we use is dynamite. So I like to think of this as giving the glacier a bit of a health check, but using dynamite as our sound source, which I really enjoy because I get to play with it. And it works like this. So we have our dynamite sound source. We send it down into the ice and it reflects back off the bedrock underneath. And we can then detect those reflected sounds in exactly the same way as you would with your ultrasound scan on the surface with these sound receivers called geophones. And this picture here is one of those explosive sources going off on the ice in Antarctica. So we do this again and again, and eventually we can build up a picture, just like any kind of body scan, of what's going on inside and also underneath the ice. Now, unfortunately, we were supposed to be there about now collecting the data, but coronavirus has put a halt to that. So I've got some data a colleague collected in a similar area a few years ago to show you, just to give you an idea of what it looks like. So here we go. This is one of these scans through the ice into the glacier. And what you can see here, this black line, is actually the bed. So it's between the ice above it and the rock below it. And so we've made an image of what we can see, what's going on at the bottom of the ice. We can see the shape of the rock underneath. We can see some differences in the material that's underneath in the bed. For example, here is different from here. And we can also see some layering inside the ice, which is really useful to tell us about how the ice is flowing. So hopefully, fingers crossed, this time next year, we'll be going to this particular area and collecting more of this data to try and answer some questions about that area. Now, because I don't have any great data to show you today, I thought I would show you a little bit of data from one of my colleagues from the MELT project, which is looking at this area here, this area where the grounded ice starts to float. And they had
Emma,
a
maybe just quickly, there's a little question, how far does those big ice tongue actually extend into the ocean? How thick is it maybe on top? Maybe you can just say 2 words about that.
Yeah, so these ice tongues like this, these ice shelves, they're quite deceptive because most of them is below the water. So about 1/9 is above the water and the rest is below the water. How far they extend, this is a good question. I can't remember exactly for Thwaites Glacier, but they can be hundreds of kilometers. So between this point and this point could be hundreds of kilometers. It could, in the case of Thwaites, it's less, but I can't remember exactly how much. But yeah, really, really thick bits of ice. They can be from top to bottom, several hundred meters. Yeah, I just wanted to show you a little project that, I say project, a scientific survey that a colleague has done in this area here, right underneath the part of the glacier where it starts to float. So they had a really cool method. They use this really narrow little robot called IceFin, which was designed at Georgia Tech University. And they managed to get this into that area right between the floating and the grounded ice by drilling a hole all the way through and then putting this robot down into that hole. So if I just go back to this diagram, they drilled from the surface of the ice all the way through using hot water. So you can melt ice with hot water, which is really convenient. Drilled all the way through and put this robot into the water there. And when it got down to the bottom, it was able to swim around a little bit and take some pictures with a camera of what was going on in that area. And this is the first time they've ever been able to do that. And I think it's something glaciologists have wondered about for years and years, trying to understand what happens in this small area. And this is the photos they got. So admittedly, there's quite a lot of brown here, which maybe doesn't look too exciting at first, but from the perspective of an ice scientist, a glaciologist, this is really, really exciting. So this is the bottom of the floating ice. And you can see there's lots and lots of different sediment and rocks in there, which we didn't know about before. This is the seawater underneath. This picture here is actually right at that point where the ice and the bed of the seabed meet. So you can see the material that's on the sea floor. You can see there are rocks down there, and you can see what the bottom of the ice looks like. And then again, this is when the robot was turning around and coming back out, it could see the bottom of the ice shelf again with lots of these little stones in it. And all of this evidence starts to tell us a bit about how the ice is moving and also the material that it's sitting on. Because of course, if it's sitting on something very hard or something very soft, it makes a difference as to how stable it's going to be sitting on that piece of bedrock. So that's most of the science part of this talk. I just wanted to give you a few impressions of what it's like to live and work in Antarctica.
So Emma, before you move on, we've got a quick question about this really cool melt project. In particular, someone is curious about how long it actually takes to melt that amount of water. So how long does that kind of hot water drilling take?
Yeah, so it depends a lot on your drill. When you're drilling a hole, it really depends on how big you want the hole. So if you're drilling a very narrow hole, you can go very quickly. If you're drilling a nice wide hole to get this robot down, it can take quite a long time. I don't know how long it took them to drill this one exactly, but it'll be a matter of days to get down into the bottom of the ice, and it depends how thick it is as well. So
great, thanks.
Yeah, so when you go to Antarctica, you're going to a really remote place, and getting there is quite difficult. So when you go there, you go and you stay out in your field camp, so in Thwaites Glacier for quite a long time. And the way we get to this particular area of Antarctica is a little bit difficult because it's actually really far away from any of the research stations on the continent. So there are, I just need to go back one slide, a minute, there we go. There are lots and lots of research stations around Antarctica that are run by different countries. Rother is the British station up here, and McMurdo is the US station. And because this project is joint between the UK and the US, we go in using both of these stations, and we arrive from, for example, here you would arrive flying from New Zealand, here you would arrive from South America, and then you get in one of these little red planes, a twin otter, and you fly down in several hops down to get to your field camp. And the reason you have to make several hops is they don't hold very much fuel, these planes. So you actually have to stop in the middle of nowhere like this and refuel your plane from one of these oil drums you can see in the background, which is a really cool experience. And being inside one of these planes is really fun. So this is what it looks like inside. This is me and my colleague. And they're really tiny. I think in this flight, it was just the two of us and some cargo, and that was all you could fit in the plane. But of course, you get an amazing view from the window of the flat ice and some mountains in the background. So when you get there, there's nothing there. It's the middle of nowhere. So you sleep in a tent, which is pretty cold. But luckily, we have a really nice set of sleeping systems to help us stay warm. So you have one of these foam camping mats with a really thick air mattress on top, and then a sheepskin on top of that, which is something I think is from the early days of exploration. So from the kind of Scott and Shackleton era, this was the kind of thing they might use, a sheepskin. And this is just the view from the door of your tent out onto Antarctica. Everyone always asks me this question, so I thought I'd better include this. Where do you go to the toilet in Antarctica? Well, this is an Antarctic toilet. It's a bucket dug down into the snow with a seat over the top of it inside a tent. So that is the answer to that question. It's actually quite comfortable. It's not too bad. And because it's December, I thought I'd just pop in a picture of Christmas in Antarctica. So this was 2014. These are the people I was working with at the time. And this is us having our Christmas dinner. And then we put Christmas, which was made of something not quite the same as what you hear, but still quite festive. So we enjoyed that. So that brings me to the end of my talk. And I just wanted to put up a few links of further information in case anyone wants to know more about Thwaites Glacier. I can really recommend the BBC News website. One of the journalists from BBC came out last year or earlier this year and spent some time with scientists out there and made some really nice reports and took some really good photos. Also, the link I mentioned earlier, if you go to this website, there's lots of information and some really nice talks that are going on tomorrow and recorded talks from earlier in the week. And then for general science about Antarctica and glaciers, this website run by one of my colleagues is really, really good. So that's the end of my talk. Before I finish and take questions, I'd just like to put up this little advert for next week's talk. So same time, same place. The talk is by Geisha Kraus and it's titled Wie nachhaltig ist die Agenda Blaues Wachstum der EU. So yeah, I hope my my German was okay, and I look forward to seeing the talk next week.
Yeah, thanks a lot, Emma. And your German is, of course, beautiful. It's perfect. Thanks a lot for this really nice presentation. This is lovely pictures. I think my favorite one is the Christmas tree. That looked really cool. Yeah, so we had some more questions in the chat, and I go for the one from Zebra Twist. She or he is saying that it's fantastic pictures and asking if you observe any marine life close to the boundary below the ice.
Yes, that's a really good question. So
maybe one more thing, you can just, I think you can stop the, oh, can you stop sharing the screen now?
I will give it a go. Let me just, yeah, I can do. There we go.
And we can talk
yeah, so you get a lot of marine life around the very edges of Antarctica. So that's where you see things like seals, penguins, whales. But actually under the floating ice, you do also get marine life. I'm not a biologist, but we have pictures we've made under a different ice shelf, not under this one, where we've seen starfish, I think sea sponges, lots of krill, which are the tiny fish that a lot of the marine life in Antarctica feeds on. So there's a lot of life underneath these ice shelves, and we're just starting to understand a little bit more about it.
Yeah, thanks. And just one more comment, because it's so nice. Walter Tanner just wrote, I could take this kind of lecture for hours. So such a big compliment.
That's really, really nice to hear. That's made my evening.
Yeah, thank you very much, Emma. That was incredibly well explained. You described everything wonderfully, and I followed it all, which is unusual for science talks. So thank you very much for that. And pictures, of course, usually help, especially in Antarctica. I have a question about the location of your project. So you're looking at the sort of shear interface between the fast-moving ice and the slow-moving ice. Mm-hmm. Does that location tend to change over time, or have you seen that it's a pretty constant place? Or maybe there aren't enough measurements to even answer that question.
So that's actually a really great question, because it's one of the questions we're trying to answer. So we don't know yet exactly how long it's been there, but we hope that we can get some indication from our measurements if it's been stable in the same place for a long time or if it's moved. And that'll be really important for the future, because of course, if it can move a lot, it could move across, and you could get much more fast flowing ice in the center, which would mean it would drain much more quickly. One of my colleagues on the project in the shear margin has been using a different technique. He's been using a radar system to go across the margin, and he thinks he sees some indication in there that there could have been movement, but we're not 100% sure yet.
Okay, and so just one quick follow-up. Like, is that instabilities you're looking for in the ice? I mean, how can you tell if there has been movement?
So as ice flows and moves, the tiny ice crystals inside the ice, they actually move and rotate and align with the stress that's caused by the ice flowing. So if you can have a look and see what kind of alignment the crystals have, you can get an idea of how the ice might have been flowing in that particular place in the past. I'm trying to think of an analogy, but yeah, it's a difficult one to explain. But you can, by looking at how the sound waves and the radar waves interact with the ice, you can get an idea of what might have happened in that area in the past.
Great, you didn't need an analogy, you explained that brilliantly, thank you.
Yeah, thanks, Emma, that was brilliant. About the analogy and the ice crystals, if someone's interested, I gave a talk about that here on the same channel some months ago, so maybe you can take a look at that and might get a bit clearer. But there was also another quite interesting question about the explosives. So how many do you have to take? How does it work on the ice? Maybe you can tell us about that.
Yeah, so obviously transporting explosives is a little bit complicated. There are kind of two parts to the system. There's the detonator, which is the part that you really that really explodes first. It's the part that ignites and lights all the rest of the dynamite. And then there's the part that really gives it some oomph, like some strength. And those two parts on their own don't really do anything. It's when you put them together that they become explosive. So you take these two parts and you transport them completely separately. So they should never be transported, for example, in the same plane or in the same, you can transport them, I think, on the same ship, but not in the same location. So at two different ends of the ship to get them down to Antarctica. How much do we take? So each shot, so each explosive we make is usually about 300 grams of explosive. And I guess, well, it depends how many you want to do. We're hoping to do a couple of hundred of these explosions for our survey. So quite a lot, like, yeah, many kilograms of explosives.
Yeah, cool. That's crazy, actually. Yeah, when I saw your pictures from the ice, I mean, I think people can come up with a lot of different questions. I loved your toilet. I mean, that was really cool. But maybe you can tell a bit how cold it was actually getting, and then yeah, and how a bit more about the life on ice there. How many people are you there working in this camp, and do you have some social life? Do you wash yourself sometimes, something like that?
Yeah, so it's a bit strange going there for the first time because it's completely different from normal life. What was your first question? Maybe I can just talk about camp life in general. So yeah. How cold it gets, yeah. So you usually start your field work. So you do your field work in winter, European winter, which is summer in Antarctica. And so you usually start around about October, November, and go through maybe until February, March at the very latest. And right at the beginning, so it would be the kind of spring in Antarctica, it's still pretty cold. So in October, it's about -35 to begin with, which is really, really cold. It's so cold, like the hairs in your nose freeze when you try and breathe. If you, I don't know, spill some of your tea or your coffee, it freezes instantly. So it's pretty cold, but it does get a lot colder in the winter in Antarctica. So I think we get the lucky job because we go in summer. In the camp, there's, it depends a little bit on the project, but there's probably between 10 and 20 people. But it'll depend on the project you're working on. And the last field season I did in that part of Antarctica, we didn't wash at all for about 8 weeks, which sounds really disgusting. But I think when hopefully we go next year on this Thwaites Glacier project, it's going to be a little bit more luxurious. So I'm hoping that we might have a few more opportunities to wash.
Yeah, I mean, I think when you don't undress, I mean, you don't need to wash, right?
Yeah, kind of, although, well, what's really interesting is when it's really cold, you don't really smell very much, as in you can't smell very much. Nothing has a strong flavour, which means you can't smell yourself either, which is really good.
Perfect.
Yeah.
Great, Emma. Another sort of question about living on the ice. I've heard of entire Antarctic campaigns that have been effectively ground to a halt because of the weather, especially if you are not one of these camps. Have you been pretty fortunate, or are you able to set up your field camp with tents effectively, so you can do your sampling almost regardless of the weather?
So yeah, I've definitely experienced some pretty bad weather in Antarctica. You get a lot of very, very windy weather, which can be a real problem when you're in a tent. So the last time I was in that part of Antarctica, we had a massive storm over New Year, and actually one or two of the tents got ripped a little bit. And luckily we had other places people could go. So we actually had a big kind of shipping container on skis, which was our kitchen, and that was a little bit more secure. So it can get a little bit scary, especially when all the snow gets blown about and you really can't see anything. You can't see your hand in front of your face, and then it's yeah, quite scary because you can't really see where you're going at all. For the work we do, we can only really do it when there's not much wind, because we're recording sound waves. And so if there's a lot of wind, you want to record your explosion reflecting off your bedrock. But actually, if it's windy, all you record is the wind noise on the surface, and it's not very interesting. So yeah, we can only do our work in good weather, which means if the weather's bad, usually we help with someone else's experiments that can be done in worse weather. But there's always something to do.
Yeah, you just briefly touched it. I was wondering if you're doing other side projects while doing your seismic measurements, or is it just you guys doing explosives and having fun, and all the other guys are stuck at a station or somewhere else?
No, so there's usually a lot of different things going on in one field camp, because it's so difficult to get there that you make the most of all your time there. So there'll be lots of other measurements going on in the same area. Some of them will be using this radar system that I briefly mentioned earlier, and some other what we call geophysical measurements. So looking at the physics of the ice and how we can kind of understand a little bit more about the structure of the ice crystals, for example.
Yeah, Emma, as a physical oceanographer, I'm of course interested in the submarine you are using, or this project you just told about. And I mean, I know that usually the most difficult part with these little submarines is how to to make them go where they should go. Like, you need some reference, or they need to have, I mean, they can't just use GPS since they are on the ice and stuff. So how does that work, and how do they get them out? Or did you say that, or how? Yeah.
So it was maybe a little bit confusing. There's the one that I showed pictures of that went under the ice. It wasn't, it was on a cable. So okay. It didn't go off completely on its own. Although, yeah, I haven't actually seen it in real life, so I don't know too much about it. But they do use, from the ship that's parked in front of the floating ice shelf, they use these autonomous ones, so the ones that go on their own. And I know they have got lost in the past. I'm not sure what they've changed, but they've definitely improved some of the navigation and some of the technology quite a lot. So they hopefully don't get lost this time.
Okay. And do you know what kind of measurements they do? It's probably salinity and temperature, so they want to describe the water masses beneath, but do they also measure some kind of biological things, or what's?
I'm not sure about biology. I think they're also making scans of the shape of the cavity that's between the ice and the seafloor. But I guess, like with everything, you make as many measurements as you can.
Yeah. Okay. Yeah, cool. Thanks a lot. I think there were no more questions in the chat, just nice comments, like at least you don't need a polar bear watch. And and then someone saying that's a really fortunate combination, no washing possibilities, but also you don't smell too much. Yeah, that's pretty good. Maybe that's a nice final word. No, thanks a lot, Emma. I think it was a fantastic talk, and it's also great to see again that people watch also the English version of Science in the Living Room. Or how did you watch?
Sitting Room Science. That's, I think, what we decided was the best English translation.
Sitting Room Science?
Sitting Room Science, yeah.
Okay, so we will think about that one then for next time. Okay, yeah, for everyone watching, you are welcome to add more comments and of course also a like if you like. And we will answer your questions then later. Emma, thanks a lot again. And to everyone, hopefully see you next time when Gesche Krause is telling us something next time in German again. Okay, so then all have a good evening. Oh, we should cheer. I think, now
Right.
It's time.
Cheers.
For cheers. And I will put our nice jingle to it. Oh no, I first need to. Well, wait. Okay. Now. Wissenschaft fürs